Dear students, I'm very happy to see you in this video lecture on the course code U18Pcit701 course in wireless network. And I'm D.Rukmani, Assistant Professor in the Department of Information Technology, working in Bharat Institute of Higher Education and Research, going to deliver you the video lecture on the topic wireless LAN, wireless local area network. So the wireless local area network, we are going to see about the introduction, wireless LAN technologies, IEEE 802.11, system architecture, protocol architecture, 802.11b, 802.11a, HyperLAN, W8M, PRAN, HyperLAN, Bluetooth architecture, WPAN, IEEE 802.15.4, wireless USB, Zigbee, 6 low PAN, wireless hub. So these are the topics we are going to see under the wireless LAN. Now we are going to see about why wireless. The benefits under wireless, which is mobility. This is ability to communicate anywhere. Easier configuration with setup and low installation cost. Easier to maintain. Solutions in areas where the cables are impossible to install. Example, hazardous areas, long distances, etc. The difficulties we face in wireless is a communication medium which is a free space. Noisy and unpredictable channel. Broadcast channel, more users will be having a less bandwidth per user. Equipment cost is high, limited bandwidth, and wireless communication is influenced by the physical obstructions, climatic conditions, interference from other wireless devices. So these are the things why we need wireless. Wireless transmission introduction, which provide an excellent high-speed and reliable data communications in built-in or the campus environments. The wireless devices transmit using one of the following signals such as IR and RF, which is an infrared and RF. The infrared TX, which is a light-based TXM using 900 nanometer wavelength. It uses a laser as a TXR and a photodiode as an RXR. It requires a direct LOS for good TX, cannot penetrate to the walls, no electrical interferences occurs, it requires a low bandwidth, no need for license. Next is the UHF narrowband TX. It supports both unlicensed band and the licensed. The unlicensed band contains 430 to 450 MHz and the licensed band contains 450 to 470 MHz. And the power level is about 2 watts. The comparison between the infrared versus the radio TX. The comparison, infrared, which uses an IR diodes, which diffuse the light, multiple reflections on the walls or the furniture, etc. Whereas in radio, which is typically using the license-free ISM band at 2.4 GHz. The advantages in infrared, which is simple, cheap, and available in many mobile devices. It has no license needed. Simple shielding is possible in infrared. Whereas in radio, the advantages is experience from a wireless WAN and mobile phones can be used. The coverage of large areas, which is possible here, the radio can penetrate through the walls or the furniture, etc. The disadvantages. Here, the interference by the sunlight, heat bands. Many things shield or observe the IR lights, which has a low bandwidth. Disadvantages in radio is it contains a limited license-free frequency sources, etc. Shielding is more difficult, electrical interference. Examples of IR is IRTA, which is an infrared data association interface available in freeware. Whereas in radio, the example is many different products are needed. Spectrum systems. The spectrum technique spread the information over a very large bandwidth, specifically a bandwidth that is much larger than the inverse of the data rate. The different impulses can be spread across the spectrum in different ways. So this allows the multiple users to transmit into same frequency band simultaneously. So the receiver can determine which part of the total contribution comes from a specific user by looking only at the signals with the specific spreading patterns. The types of spectral systems are FHSS, which is a frequency hopping spread spectrum. Next is the D.Rukmani, which is a direct sequence spread spectrum. We are going to see each one in detail. IEEE 802.11, which is a wireless LAN, which is also abbreviated as WLAN, which connects the single mobile stations to the multiple landline systems. It also connects the fixed location computers to the internet. It's very flexible within their reception areas. The ad hoc networks do not need planning. No wiring difficulties in IEEE 802.11 WLAN, that is historical buildings or the firewalls. More robust against disasters like earthquakes, fires. Covers an area up to 100 meters. The data rate from 700 kbps to 55 kbps, Mbps. Operating frequency is about 2.4 to 2.5 GHz. The classifications of 802.11 are the infrastructure network and the ad hoc network. The comparison between the infrastructure versus the ad hoc. In the infrastructure network, see the diagram, we'll be having a interface between the nodes, that is an access point will be there in between the nodes. It's the infrastructure network. Whereas in ad hoc, we don't have any access points. So this is what the main difference between the infrastructure versus the ad hoc networks. 802.11 architecture of an infrastructure network. By the name itself, it will be having an access point in between. So see here, the STA station 1, it contains of about 802.11 LAN BSS1, that is a base subsystem. So here we'll be having an access point, that is a distributed system which is connected to the other nodes, station 1 and station 2, and we'll be having an ESS, which is an extended service set. The basic service set versus a BSS, which consists of some number of stations executing the same MAC protocols, and it will be competing for the access to the same shared wireless area. A BSS may be isolated or it may be connected to a backbone distribution system through an access point. So here the access functions as a access point functions as a bridge and a relay point. So in a BSS, the client stations do not communicate directly with one another. If one station in the BSS, that is a basic service set, wants to communicate with the another station in the same BSS, the MAC frame is first sent from originating stations to the access point, and then from the AP to the destination station. So here, a MAC frame from a station in a BSS to a remote station is sent from the local station to the AP, and then it is relayed by the AP over the DS on its way to the destination station. An extended service set, which is an ESS, consists of two or more basic service sets, that is BSS, which is interconnected by a distribution system. Which is typically the distribution system is a wired backbone LAN, but it can be communicated to the any networks. WLAN services are the association, authentication, de-authentication, disassociation, distribution, integration, MSDU delivery, privacy, and reassociation. So these are the wireless LAN services. IEEE 802.11 protocol or the layered architecture. So here we'll be having a mobile terminal, that is an application layer. The mobile terminal will then connected to the access point. From that we'll be having, and this is called as an infrastructure network. So here we'll be having an application layer in that the physical and the MAC layer and the LLC. The physical and the MAC layer, which is then interconnected with a is the access point layer, that is a middle layer, intermediate layer, whereas the another partition which is then compared to the another application layers. So here the intermediate point is divided into two. One is connected to the other end and other is connected to the next end. So this is called the protocol or the layered architectures. So IEEE 802.11 layers. They are physical or the PH5 layers, MAC layer. Under the MAC layer, we have two types. That is a MAC sublayer and the MAC management sublayer. Now we are going to see about the physical layer. So it consists of encoding, decoding, modulation or demodulation. Whereas in MAC layer, we have a MAC sublayer and the MAC management sublayers. The MAC sublayer, it contains a fragmentation and the reassembly of the packets. Whereas in MAC management sublayer, the roaming, power management, registration and connection management is possible. The physical layer is further divided into sublayers. The physical layer, which is further divided into sublayers, they are MAC layer, PHY convergence procedure, which is PCLP, and the PHY medium dependent, which is PMD, and at last will be the management layer. So here the PLCP, here the carrier sensing and it will convert the data frame and it carry the management information too. Whereas in PMD, which is a physical medium dependent, which defines the modulation and the coding techniques for signaling. Physical medium for WMAX, which is a frequency hopping spectrum, direct sequence spectrum, physical, and the diffused infrared, which is a baseband. We are going to see HFHSS. So two data rates for transmission net 1 and 2 Mbps. It will be available at channel 78 with a bandwidth of 1 GHz. The modulation technique is GFSK, Gaussian frequency shift keying. So each basic service set will select one of the three patterns of 26 hops with the three groups. So here we will be having a three groups which contains of 76 channels. That is, group 1 contains 0 to 75, group 2 contains 1 to 76, and group 3 contains 2 to 77. So three groups. So here it is connected. Here we will be having a bandwidth of 2.4 to 2.48 GHz. And this is the frequency of this spectrum, physical transmitter and receiver block diagram. So here we will be giving an input, that is PSU as 00111001 to the data whitener. From the data whitener, it goes to the symbol mapping. From there, we will be getting a Gaussian shaping filter. At last, we will be getting the output of Gaussian frequency shift keying modulator. So here, the modulator from the Gaussian modulator, we will be doing a demodulator with the help of the hop timing recovery, that is a data clock. By that, we'll be getting the data D whitener. At last, we'll be getting the output as PSDU, which is a physical transmitter and receiver of frequency hopping spectrum. So in frequency hopping spectrum, PHY, the data transmission over a media is controlled by the frequency hopping spectrum PMD sublayer as directed by the PHSS PLCP sublayer. The binary information bits will convert them into a array of RF signals by using the carrier modulation and FHSS techniques. Next will be the data whitening, which is used for PSDU before the transmission to minimize the DC bias on the data. If long strings of ones or zeros are contained in the PSDUs, the physical stuffs a special symbol every 4 octaves of the PSDU in a PPDU frame. So this is a PHSS physical PPDU frame format. So here we'll be having a PLCP preamble, PLCP header, at last with the whitened PSDU. The PLCP preamble contains a synchronous frame and SFP, which is a start of PSDU frame. Whereas the PLCP header contains PLW, which is a PLCP length word, PSF, which is a PLCP signaling field, checker error. Next, last the whitened PSDU. The synchronized field contains a string of alternating zeros and ones patterns and is used by the receiver to synchronize the receiver's packet timing, and it will correct for the frequency of this. The SFP field will contain the informations making the start of the PSDU field. The PLCP length word, that is PLW field, specifies the length of the PSDU in octaves, and it is used by the MAC layer to detect the end of PPDU fields. The PLCP signaling field, that is PSF, identifies the data rate of the Whitening PSDU ranging from 1 to 4.5 megabits per second in the increments of 0.5 megabits per second. The header error check field, which contains the result of a calculated frame check sequence from the sending stations. The PHX's PMD uses two-level Gaussian frequency shifting keying, that is GMSK modulation, to transmit the PSDU at the basic rate of 1 Mbps. 4-level GFSK, which is the optimal modulation scheme, which will enable the Whitening PSDU to be transmitted at the higher rate. Direct sequence split spectrum BIHER. The encoding scheme that is used is PBPSK, which is a differential binary phase shift keying, will send 1 or 2 bits per symbols. The total bandwidth is 2.4 GHz, which is divided into 11 channels with space by 5 MHz. The DSSS will communicate non-overlapping pulses at the chip rate of 11 NCPS, which occupy 26 MHz. It contains a frequency of 2.4 GHz to 2.462 GHz. The data transmitter and receiver of DSSS. So here the PPDU has given as an input to this scrambling. From there it will be giving to the spreading. The spreading will be combined with the 11-bit barcode code to get the output as a mask filling. At last we'll be getting the modulation output. So from there we'll be doing a despreading and we'll be demodulating those inputs. By demodulating, we'll be descrambling and we'll be getting the PPDU with the help of time clock recoveries. So this is what the kind and receive DSSS PPDU. So here we will be using a 11-bit barcode code which is used for splitting. So in transmitter, the 11-bit barcode code is applied to the module to adder together with each of the information bits in PPDU. The output of the module to adder results in a signal with a data rate that is 10 times higher than that of the information feed. So the result in the frequency domain is a signal and that is spread over a wide bandwidth at a reduced power level. So at the receiver end, the DSSS signal is convolved with the same 11-bit barcode code and it will be correlated. The same format for DSSS, which is will be containing of PLCP preamble and PLCP header. At last in PHSS, we'll be having a Whitening data. Here we'll be having an NPDU. The synchronized field, it contains of 128 bits, XFP field, which is the start of the PPDU frame. It's the signal bits which contains the header signal, service length, and CRC. At last is the NPDU. The synchronized field, which contains of about 128 bits, symbols in length, and it contains a string of 1S. The receiver uses this field to acquire the incoming signal and to synchronize the receiver's carrier tracking and timing prior to the receiving the XFP. The XFP field contains the information to mark the start of the PPDU frames. The signal frame, which specifies the data rate at which the NPDU portion of a frame is transmitted. The length will indicate the length of NPDU field by specifying the number of microseconds necessary to transmit the NPDUs. The CRC fields are used for error checking and correction. PPDU, which is a physical protocol data units. PSDU, which is a PLCP service data unit. MPDU, which is a MAC protocol data unit. Next, the third type is, which is a diffused infrared, that is diffused IR. The PMD of BIHER, that is a diffused IR, will operate based on the transmission of 250 nanosecond pulses. So these pulses are generated by switching the transmitted LEDs on and off during duration of the pulse. The peak power of pulse is 2 watts and the wavelength is 850 nanometer to 950 nanometer. So here the 16 ppm and 4 ppm modulation techniques at the data rate of 1 and 2 Mbps. So in this 16 into 250 nanoseconds, which we get a 4000 nanosecond carrier in the 4 bit of information that supports 1 Mbps. PLCP frame format for BIHER, which is a diffused infrared. So here we contain a PLCP. In that we'll be having a preamble, header, and NPDU. In the synchronized field, we'll be having 57 to 73 bits, whereas in SFP we'll be having only 4. The data rate is 3. and DCLA, which is 32, that is DC level adjustment sequence. Length is 16. FCS, which is error check correction, and lastly NPTU, which is greater than 2,500 bytes. IEEE 802.3 carrier sensing. So the receiver reads the peak voltage of the wires of the cables and compares it against a threshold. The physical sensing is through a CCA signal produced by PLC. The real sensing mechanism is done by two methods, that is, which detects the grids in air and checking in RSS. The detection method is reliable than RSS because of interference. The virtual carrier sensing, which is based on network allocation vector, and NAV is supported by the RTS or CTS and PCF mechanisms. Length field in the map layer is used to specify the amount of time that must elapse before the medium can be fed. So this is a block diagram for the map layer. We will be having an LLC, and from the LLC we will be having units, that is contention free service and contention service. The contention free service will go to PCF, which is a point coordination function, whereas the contention service comes from LLC and goes straight to the DCF, which is a distributed coordination function. From there it goes to FHSS, BIHER, infrared, OFDM, DSSS, and DSSS OFDM. Next, the layer 2 function, which is a MAC layer. The medium access function, which is a MAC layer. So on transmission, assemble data into a frames with the address and the error detection frames. On reception, the disassembled frame and it will perform an address recognition and error detection. It governs the access to the LAN transmission mediums. Next will be the logical link control, which is LLC. Will provide an interface to the higher layers and it will perform the flow and error control. The lower sublayer of the MAC layer is the DCF, which is a distributed coordination function, which uses a contention algorithm to provide access to all the traffics. The PCF, which is a point coordination function, which is a centralized MAC algorithm used to provide the contention-free service. The PCF is built on top of DCF. DCF, which is a distributed coordination function, which uses an interframe space, that is IFS and the CSMA. Steps including DCFR, a station with a frame to transmit senses the medium. If the medium is idle, it waits to see if the medium remains idle for a time equal to IFS. If so, the station may transmit immediately. If it is busy, the station defers the transmission and continues to monitor the medium until the current transmission is over. Once the current transmission is over, the station delays another IFS. So if the medium remains idle for this period, then the station backs off the random amount of time and it again senses the medium. If the medium is still idle, the station may transmit. During the back off time, if the medium becomes busy, the back off timer is halted and it resumes when the medium becomes idle. So if the transmission is unsuccessful, which is determined by the absence of an acknowledgement, then it is assumed that a collision has occurred. PCF, which is a point coordination function. This is an alternative access method implemented on top of PCF. The operation consists of polling by the centralized polling master, that is a point coordinator. The point coordinator makes use of BIHER when issues polls. During the first part of this interval, the point coordinator issue polls in a round-robin fashion to all stations conferred for polling. When a poll is issued, the polled station may respond using SAFS. If the point coordinator receives a response, it issues the another polls using PIFS. The point coordinator then idles for the remainder of the superframe, allowing a contention period for asynchronous access. MAC layer contains a MAC sublayer on the MAC management sublayer. MAC sublayer defines the access mechanism and the packet formats. MAC management sublayer, which has a roaming support, power management, as well as the safety. The MAC sublayer accessing mechanisms are the contention methods and contention-free methods. So in contention method, we will be having CSMA or CA. Whereas in contention-free, we will be having RTS or CTS, which avoids the hidden terminal or the exposure terminal problems. Next, the PCF, which is assigning a priority for the packet transmission based on polling. This is a time-bounded application. So this is a frame format. Here we'll be having SAFS, FAFS, and BIFS. Next the contention deferred. Next the BIFS. Next we'll be having a contention window. At last we'll be having the medium PC. Okay, so the station transmits the packet immediately by sensing the channel S2. If it is busy, then NAV is turned on by sending the back of 10 and wait for BIFS period. SAFS, which is a short interference spacing, is the highest priority packet such as acknowledgement and CPS. The PCFS, which is the second priority duration, which is SAFS to BIFS. BIFS means which is a DCFIFS, which is the lowest priority and the longest duration. So after the completion of a transmission, each station has to wait based on its priority. So this method will reduce the collision, but it can't eliminate it. So this is an implementation of CSMA, CA, or acknowledgement. So see here, when an access point receives a packet of data, it waits for the SAFS and then it will send the acknowledgement. Because SAFS is less than BIFS. All other terminals must wait until the transaction of acknowledgement to mobile station is completed. Implementation of RTS or CTS mechanisms. If the channel is free, it sends RTS, which carries the source, destination address, and the data. Destination station replies CTS, that is 16 bytes after SAFS period. The source terminal sends the data after SAFS period. Finally, the destination reply acknowledgement after receiving the data. Station 3, it hears the RTS or the CTS communications for the entire period by setting the NAV signal on. So after the completion of transmission, the NAV is terminated, opening the contention for other users. Next, the PCF operations. So here we'll be having an NAV and the contention free period and the contention period. It's PCF burst and DCF burst. At last, about the variable length in CFP period. So the frame format for map. Here we'll be having a data frame control, durations or ID, address 1, address 2, address 3, sequence control, address 4, frame body, at last the error check action. The frame control will indicate the type of a frame and it provides the control information. The duration of the ID, which is a connection ID, indicates the time in microseconds. The channel will be allocated for the successful transmission of the map frame. In some control frames, this field contains an association connection identifiers. The sequence control contains a 4-bit fragment number subtype used for fragmentation and reassembly, and the 12-bit sequence number used for number frame sent between a given transmitter and the receiver. The frame check sequence, which is 82-bit cyclic redundancy check. Next will be the frame control field. So here we'll be having a protocol version, type, subtype, 2DS from DS, more fragmentation, retry, power management, more data, WVP, and reserve. Map management sublayer. So it is used to establish a connection between the stations and the APs. So it provides an accessing mechanism for mobile stations. The functions under map management sublayer are the registration, handoff, power management, and security. The first we are going to say about registration. So here the AP periodically sends the beacon frame to mobile station for timing synchronization. So it contains PSS ID, RSS, roaming, timestamp. The beacon used to identify the AP and the network. The association request, here the mobile station sends this request to AP. Whereas the association response, the AP grants the permissions to the mobile station. Handoff, which is a mobility environment. So here we'll be having a node transition, BSS transition, ESS transition. The node transition, the mobile station is static or moving, but it's inside the BSC. Whereas in BSS transition, the mobile station moves from one BSS to another BSS, but in same ESS. The ESS transition, the mobile station moves from one BSS to another BSS, but in new ESS. Next is the connection registration. You'll be having a reassociation service and a disassociation service. So in reassociation service, here the mobile station moves from one BSS to another BSS, but in same BSS. Hence, the mobile station sends a request to distributed system via the AP. It is diassociation service, which is used to terminate the association for the mobile station when it leaves from BSS. This is a handoff procedure. Here we will be having a strong signal, weak signal, scanning for handoff. Next will be our probe request, probe response. Next, we'll be choosing an AP with the strongest response, reassociation request and reassociation response. At last, we'll be having an IAPP indicates the reassociation to the old access point. Next here, the mobile station moves from access point to the access point. So it sends a beacon signal from AP to MS, whereas MS logs the APL1 who has a strong RSS. Here the MS lies in border between two APs, hence it sends the probe signal to all the APs. So all the AP will reply probe via the RSS to MS. The MS select the AP by a strongest signal. The MS will send the reassociation request to AP, whereas the AP reply the association response to the MS. The handoff message is informed to the old AP1 and AP2 via the inter-access point protocols. Next is the power management. So when a station is idle, it dominates the LAN or router power consumption. So it is important to put the MS in sleeping mode. It will buffer the data in AP, send to MS in awaken. The mobile station uses the power management bit in a frame control flip to announce its active or sleep mode. With every beacon, the team sends list of stations has buffer data. Now AP send the data to MS. Security. Open system authentication or a secret key. Next is the shared key authentication. So here we'll be having a request station and authentication ID. The second station, the first station will send the encrypted challenged text as a response. The second station send the authentication results. Thank you.